Hello and welcome to today's lesson on hypothesis testing. Now I'm going to give you a little bit of warning. I do think that this is one of the harder topics for statistics in the AS level. But as long as you understand the concepts of this, it does become pretty easy. So as long as you understand kind of what we're actually talking about and what an actual hypothesis test is, that's kind of the majority of kind of your understanding. So let's have a go and go through. I'm actually have to go to make this big for all of these because I think it's better to be able to see them. So I throw a coin 10 times. For what number of heads might you conclude that the coin is biased towards heads and why? So let's have a look at this one. So obviously our intuition is that the further away we are from our expected number of heads, i.e. 5 heads out of 10, then the more likely it is. And this makes perfect sense, really. So if we were to flick a coin 10 times, the question we're asking is for what values, or if I did an experiment, how many times would it have to come up as heads so that I can say that this coin is unbiased? Now, we expect to get 5 heads. But we know that doesn't actually always happen. We could get 6 heads, we could get 4 heads, we could get 3 heads if we flick it 10 times. But the question we're asking here is, how many heads would I have to get for me to say that the probability is so small that the coin must be biased? So here we've said 9 or 10. So what we're saying here is that if I flick a coin and I get 10 heads in a row, then I know that that coin must be probably biased. But we're also saying in this region here, if I flick a coin and I get 9 heads, then actually that coin is also probably biased. Now, it is worth mentioning here as well, any of these black boxes with a little pencil next to them, it's worth getting that down in your notes because, as I said, the ones that are in the black boxes with the little notes come up as definitions that you have to actually answer, and you get a few marks for that. So it's worth writing those ones down. Okay, I'm going to go back to full screen. So a hypothesis test is a statement made about the values of a population parameter that we wish to test by collecting evidence from a sample. So in this case here, in this context, what we're saying, we're asking, is the coin biased? So this is making a statement about the probability of getting heads. Now we're not talking about heads and tails here. We're talking about just getting heads. So we know the probability of getting heads is 0.5, and we know this follows a binomial distribution if we're doing it 10 times. Okay. So the null hypothesis, and this is really important, is the default position, i.e., nothing's changed unless proven otherwise. So what do we mean by the null hypothesis? Well, the null hypothesis is your starting point. So if I had a coin, what I'm saying here is that I think that the coin should be 0.5 probability of heads. That's my starting point there. I've got a coin. You expect it to have a probability of landing on heads of 0.5. That's my null hypothesis. That's the starting position. We'll just see that. So it's the default position that the probability of the coin is fair. So the probability of getting a heads is 0.5. So your alternate hypothesis, which is H1, is that there has been some change to the population parameter. So what do we mean by this? Well, if I was to say, I've got a coin here, and the probability of getting a heads is 0.5, and then somebody else comes along and says, well, actually, I'm going to do an experiment to prove that you're wrong because I think that your coin is biased. That statement that they've just made is your alternate hypothesis. Now, they might say it in a few different ways. They might say that I think it's biased towards heads, in which case what they're saying there is they're expecting it to land on more heads, okay, than 0.5. They could say, I expect this to be biased towards tails, in which case you'd expect it to get less heads than 5. Or you could also say that you don't know whether it's biased either way, and in which case you say that I just think that it's biased. And this is actually called a two-tailed test, which we'll come to later. So the alternate position that the coin is biased towards heads e.e. the probability is 0.5 in this case. Okay, so we in this case here, we're thinking about the fact, is our coin biased towards heads, or is the probability of it actually 0.5? And what we're saying is, if I do an experiment by flicking this coin 10 times, and I get either 9 heads or 10 heads, then I think my coin is biased. And that there is kind of your starting point of this. So we're saying, I've got a coin, and I expect the probability of my coin getting heads to be 0.5. Somebody else then comes along, or you think it yourself, you say, well, actually, I think this coin is biased. And actually, I think it's biased towards heads, so I think I should get more heads. So the question then is, how many heads would I need to get in my experiment to say that actually the probability of that happening is so low that actually this coin is biased, and that couldn't have happened if it wasn't biased towards heads? And that's the starting point here. That's really important to understand. Okay, so this next one, I'll make it big again, is in a hypothesis test, the evidence from a sample is a test statistic. So in this case here, what we're saying is I'm going to do 10 flicks of the coin. That's going to be called your test statistic. So in this context, let's have a little what they say. A test statistic X is what we observe, so the test. In this case, X, the number of heads seen in 10 throws. So what we're saying here is, I can't do it in an infinite amount of times to prove that the population parameter is 0.5, but what I am going to do is I'm going to do a test, and if I get an unexpected outcome in that test, then this coin is biased. Note that a test statistic is a distribution, i.e. across the possible things that we might observe. So here we've got a binomial distribution, and it's a binomial distribution of with 10 flicks and the probability of P. Noting that P is not known until we start to make the assumptions. Okay, so the significance level is the point at which, so the significance level can change, and you might say with this that you always want your level of significance to be the same, but actually for different tests you want to test different things. Now, your significance level is the percentage at the extremities, so 5%, 1%, where we say that actually the probability is so small that this could never happen. So if the probability is of all these things happening is 5%, then we know that this isn't going to happen. We'll come back to that in a little bit more detail. Do remember to get these down in your notes though. So we said that if we saw a number of heads within the range of outcomes that were significantly unlikely, then we'd rule out that the coin is fair and conclude that in fact it is biased. So how unlikely is sufficiently unlikely? If our significance level, and that alpha there means the significance level, so do remember that, this part here. So alpha is equal to 5%. Then we'd find the regions of outcomes where there's at most a 5% chance of one of these extreme values happening by chance, i.e. the coin was not fair. So what we're saying here is we're saying that your level of significance is 5%, which means that if all of the outcomes that were going to happen were 5% or below, then 5% is my significance that we're not going to get this. 5% is far too low of a probability. The chances of getting 5% is 1 in 20. So I'm going to say that there, 1 in 20, is too low for this to just be a fluke. Okay, that's the point. If it was 1%, then we're going to say its chance is 1 in 100, aren't we? So if I set my significance level at 1%, I'm going to say, well, 1% means that if I was to do this experiment and I get an outcome which is only 1%, then actually, it must be biased or it can't be true. That's what a significance level is. Okay, so here we've got hypothesis tests in a nutshell then. So we have some hypothesis which we wish to see as true, i.e. is the coin biased towards heads? That's our initial hypothesis. We then collect some sample data by throwing a coin, giving us our test statistics. So we do some experiment and we see the outcome of that. if the number of heads is sufficiently unlikely to have emerged just by chance, then we conclude that our alternative hypothesis is correct. So if we get loads of heads here, then what we're saying is that the chances of getting 9 or 10 heads out of 10 is so small that the coin must be biased. Now, that's biased towards heads. If it was the other way around, we could say that, well, actually, I've actually got no heads at all, in which case it must be biased towards tails, okay? Or we can do either end, but we'll talk about that with the two-tailed test a little bit later, okay? So, let's talk now about our null hypothesis and alternative hypothesis. So, it's probably worth, I'd like to get a full example down of these. I think it's better to understand it when we get a full example, but we'll start off. It's probably worth getting these down in your notes. So, let's make it big for you. John wants to see whether a coin is unbiased or whether it is biased towards coming down heads. He tosses a coin 8 times, and the number of times X it lands on head upmost. So he's done an experiment here, again with the coin, and this time he's flipped it 8 times. We said that our two hypotheses are about our population parameter. So suppose P is the probability of the coin landing on heads. So what we're saying here is, what are the two different outcomes? Well, my first one is that, which is my null hypothesis. So let's get this down then. So my null hypothesis in this case, gotta make sure I'm spelling hypothesis right. My null hypothesis in this case is that, remember H0 is your null hypothesis. So H0 is that the probability of getting heads is equal to 0.5. So that's my null hypothesis there. Okay, so your population parameter, my initial statement is that I'm going to get, the probability of getting heads is 0.5. Then I've got my alternate hypothesis. So my alternate hypothesis in this case, and in this case, it's going to be H1, which, I don't know why I put an I there, H1, okay? And with H1, we're saying it's biased towards heads in this case. So actually, we're saying that the probability of this is biased towards heads, which means that this isn't the probability anymore. We are expecting the probability to be greater than 0.5. So this is my null hypothesis, the population parameter, that the probability of getting heads is 0.5. My alternate hypothesis is that actually the probability of getting heads is 0.5. And you will always need to write these down in these questions, so do get used to them, okay? So 0.5, let's just check that, and the probability is greater than 0.5. So this is, again, remember, what I have spoken about this is the population parameter. So in this case, it's normal that a coin, and it's normal that a normal coin and the probability of heads is 0.5. That's what we're saying here in this case. Under the alternate hypothesis, H1, there has been an underlying change in the population parameter. So what we're saying here is that the coin is biased towards heads, and that means that it's going to be greater than 0.5, okay? If it was biased towards tail, it'd be the other way around. Tails, it's going to be the other way around, isn't it? It's going to be less than 0.5. In fact, we'll talk about this here. So the latter is known as a one-tailed test. And now it's one-tailed because you're only looking at one direction. You're only looking at the probability that it's biased towards heads. Another one-tailed test would be that it's biased towards tails, in which case I'd be the probability would be less than 0.5, and that's actually what they say here in this case. So the probability it's biased towards tail would be P is less than 0.5. But also, we could say that we don't know whether it's biased towards heads or tails, but we do think that it's biased. In this case, we call it a two-tailed test, and we write this. Now, we'll talk about this a little bit more later. So when we've got a two-tailed test for I, now leave that one there. We don't need to get that. That's the first question done. But if we had a two-tailed test, we'd have our population parameter, which is equal to my probability is 0.5, and then if I didn't know whether it was biased towards one or the other, what I would say is just that my alternate hypothesis is that my probability is not 0.5, okay? And that way it could be greater than 0.5, it could be less than 0.5, but we just don't know. We just don't think that our coin is right. So that's a two-tailed test, okay? So Let's have a look at this next question. Let's make it big for you so you can see and copy it down. Do get these down in your notes. An election candidate believes that she has the support of 40% of the residents in her particular town. A researcher wants to test at 5% significance level whether the candidate is overestimating her support. The researcher asks 20 people whether they support the candidate or not. 3 people say that they do. Write down a suitable test statistic. Write down 2 suitable hypotheses and explain the condition under which the null hypothesis would be rejected. Okay, so let's have a look at this one here then. So she's asked 3 people, okay, so they've done a test, they've got a population parameter. She thinks that the probability of her, she reckons that 40% of people support her with her candidacy in her local town. Now, somebody said, right, I don't believe you. I don't think that's true. So I'm going to do a test to see whether that's true or not. So in this case, write down a suitable test statistic. So your suitable test statistic in this case is when I ask the people whether they think they support her, we're going to ask, when we ask these 20 people, we're going to ask them whether they support her. So the answer to this is it's the number of people who say they support the candidate. Perfect. So that's our test statistic. So we're going to ask 20 people, I'm going to ask them, do you support the candidate? Okay, so write down part B, write down 2 suitable hypotheses. So with this part here, what we're saying is, the population parameter in this case, H0, so my null hypothesis, my null hypothesis, ... not equals, is that my probability is equal to 0.4. So that's what I'm saying. I think that my probability is, our candidate thinks that the probability of her, 40% of people want her to get the candidacy. That's what she thinks. Now, the person who is disagreeing with her is saying, let me just check, thinks that she's overestimating her support. So he thinks that the probability is actually less. So this is the population parameter. This is our null hypothesis. And somebody's come along and actually said that, right, okay, I think that actually the probability, I think you're overestimating this. And actually, I think your probability is less than 0.4. Okay? So these are our 2 hypotheses. The probability that she gets 40% is the population parameter. So that's my starting point, my null hypothesis. And then your alternate hypothesis, H1, is that actually she's overestimated that, in which case her probability is going to be less than 0.4. Let's just check those. Yeah, super. Super, yeah, brilliant. So explain the conditions under which the null hypothesis would be rejected. So in this case, what we're saying is what would we have to get in our test to say that what she is saying or what they are saying is true? And what we'd have to say is that the null hypothesis would be that the null hypothesis would be rejected if the probability of 3 people supporting the candidate is less than 5% in this case. Okay, so part C. So our null hypothesis, never spell hypothesis, would be rejected if the probability of 3 or fewer people is less than 5%. With a population parameter given probability is equal to 0.4. So what we're saying here is that I would reject my original candidate's population parameter or original hypothesis if the probability of getting 3 or fewer, okay, is actually less than 5%. Now we could do that on a calculator actually, so let's have a little look. So it doesn't ask for this here, but I am going to have a little look at it. So if I go to menu, okay, and then I go to distributions, okay, and then I go to, I'm not going to PD, I'm going to cumulative now. So binomial, go down, binomial CD to the cumulative. Now you could get your list, but actually we're only checking one thing here. So I'm going to go on to variable. So what we're saying here is that we have done the experiment, okay, and we've got 3 people, okay, 3 people have said that they're going to support her, out of, so that's X, out of 20. And we believe the population parameter to be 0.4, okay? So if I press equals on that, I actually get a probability of 1.5%. So actually the probability of this happening is 1.5%. Now, if you think about that, if I said to you the probability of picking 3 candidates, of picking 20 candidates, and only 3 of them say, yes, we support her, and actually it should be 40%, then what we're saying here is that she is talking rubbish. She's not talking any sense, okay? Because actually the probability of that happening is 1.5% there. Sorry, 1.6 it should be. We don't need that in this question here. But I'm basically doing a full hypothesis test here. But we're saying here, the probability of that happening is 1.6%. And actually, that's a really low percentage. So actually, she's not talking, she's not making sense, because the probability of getting the probability of getting 3 people out of 20 is really low on the chance if the actual population parameter was 0.4. Now we'll come back to that later. That was our first little hint of our hypothesis test there. So the null hypothesis will be rejected if the probability of 6 or more students being late to school is less than 10%. Oh, sorry, it's a 10% significance level, sorry. So less than 10% given the probability is equal to 0.05. Super. Oh, sorry, that's a different question. No, I was right, 5%. Super. Okay. So let's have a look at this next question here then. So in the UK, let's make it big for us so we can see it. In the UK, 5% of students turn up late to school each day. Mr. Hamid wishes to determine to a 10% significance level if his school, Piffin School, has a problem with attendance. He stands at the gate and finds 6 of 40 students passing are late. Write down a suitable test statistic. Write down 2 suitable hypotheses and explain the condition in which the null hypothesis would be rejected. Okay, so with this one here, the first thing we're looking at is part A. Write down a suitable test statistic. So what are we actually looking at here? Well, we're looking at the number of students who are late to school that day. So our test parameter, our test statistic is the number of students who are late to school that day. Brilliant. That's the first part. Part B says, write down 2 suitable hypotheses. So we know that the national average of this people being late is 0.5. Okay, so that's going to be my initial hypothesis. So H0 is that my probability is equal to 0.05, 5%. Okay, that's going to be my population parameter for everybody. Now, what we're saying here is if Piffin's school has got a problem with this, then we know that actually the probability of that is going to be higher. Okay, so my alternate hypothesis in this one, I keep putting an I there for some reason, is that the probability of Piffin's school is greater than 0.05. So actually the probability of this is higher than 0.5. So these are our two hypotheses. Either the school's in line with the population, in which case the probability is 0.05, or that they have got a problem with this, and the probability of this is greater than 0.05. Okay, so part C, explain the conditions under which the null hypothesis would be rejected. So in this case, we would reject the null hypothesis if when we did our experiment of 40 people, the probability of getting 6 or more students being late to school is less than 10%, given the probability is 0.05. So the null hypothesis would be rejected if from the experiment of 40 students, it is 40 students, yeah, so 40 students of the experiment of 40 students, the probability of 3, six or more students being late is less than 10%, with P equal to 0.05. Okay, I actually think this is probably harder than actually doing the test itself, because we're actually having to explain it each time. Now, again, it's not asking us to do this, but we can actually check this, because we can do it in our binomial CD. Actually, we'll come back to that in a second, actually, because this is greater than with this one. And there's a little bit of a thing we need to think about. So what we're saying, let's just check our answers with this one. So the number of students who are late to this school that day, that's what we said. Our hypotheses is that the probability that a student in the population is 0.05. And if there is a problem, that we know that the probability is going to be greater than that in the school, that's fine. And the null hypothesis would be rejected if the probability of 6 more students being late to school is less than 10%, given a probability of 0.05 in this case. So I'll make that big just so we can talk through the details. Just to reiterate again what's going on, we're assuming that the school is the norm, so we're assuming that the probability is 5%, and calculate the probability that 6 or more students will be late under this assumption. If the probability of this happening by chance is significantly unlikely, less than 10%, well, then we would conclude that the probability isn't just by chance and that the school's lateness is worse than 5%. So kind of in a nutshell with that, if we do our test and actually the probability of it happening is really small, okay, then we actually say that yes, the school's got a problem with attendance, because the chance of that happening is so small that actually the probability of children being late must be bigger. Okay, so let's move on then. So we're going to have a look now at critical regions. Okay, critical regions and values. So John wants to see whether a coin is unbiased or whether it is biased towards coming down heads. He tosses a coin 8 times and counts the number of times X it lands on head upmost. what value would lead to John's hypothesis being rejected? So we're not looking at probabilities now, we're looking at actual outcomes, and that's what a critical region is. We're saying we're flicking the coin 8 times. How many times must it be, how many heads must I get for me to say that this coin is biased? Okay, so so with this one here, the probability of getting a heads exactly 5 is only 22%. Now you might think to yourself, well, 22% is really low, so surely it's biased if you get that. But it's actually more likely to happen. If we look at this graph here going up, okay, we can work out the probability of each of these things happening. And actually, remember, the probability of all of these things happening sums to 100% or 1 in this case. And actually, because we've got 8 different outcomes here, we know that all of them need to sum to 1. Now, if I was just to do 8 divided by, well, sorry, 1 divided by 8, 1 divided by 8, if we had an equal chance of everything happening, or they were all kind of uniform, then the probability of each of them would be 0.125. But we know that actually that things are more likely or less likely to happen in this case. And actually the chances of getting 4 is higher than the chance of getting 8, and that's why it's so small. But just because it's 22%, it doesn't mean that that probability is low, because it's spread out over 8 different variables. And if we did it for 8, we'd see that it was much lower. So the probability is only low because there are lots of possible outcomes, which is what I've just said, because there's 8 outcomes there. So the probability is low because there's 8 outcomes. But 5 heads forms part of a range of the possible number of heads that collectively would be consistent with the coin not being biased towards heads. So what we're saying here is that actually 22% is quite in line with the probability of this not being biased. Now, on the other side of that, however, there are values which collectively form a range of extreme values. So there are some values here which means that the coin would be biased. So there are some outcomes of my test which means that the coin are biased. In this case, it's 7 and 8. So their combined probability is limited by the level of significance set at 5%, which means that the coin would be biased. So if I was to flip my coin 8 times and I get 7 heads, then you should be asking the question, yes, this coin is biased, okay? Because it's really unlikely for me to get 7 heads out of 8, okay? And actually that significance level is 5%. So John wants to see whether, let me make this big for you so you can see it. John wants to see whether a coin is unbiased or whether it's biased to coming down heads. He tosses the coin 8 times and counts the number of times X it lands on heads uppermost. What value would lead John's hypothesis to be rejected if the significance level was 5%? Now, you'll notice that on here, you've got a binomial table. You can actually do this on your calculator. So it's probably worth me showing you how to do that first, okay? So if I go onto menu, and I go to number 7, which is statistic there, okay? Then what we're going to be doing is we're going to go down. Now we're going to look at the cumulative distribution of this. Remember that cumulative means running total, so we're looking at all of these values together. So click on 1 on cumulative, and we're going to go on to list, okay? So click on list. Now in that list, we're going to write down all of our different values. So it's going to be, if we're flicking this coin 8 times, okay, then our outcomes are going to be 0. Okay, so 0, getting 0 heads, 1 head, 2 heads, 3 heads, 4 heads, 5 heads, 6 heads, 7 heads. If it was to do 8 on there, okay, if I was to do 8 on there, then we know it's going to be 100%. So I press then 80, okay, and then I press equals. And now what it's asking for is, what's the amount of times that you've done this test? Well, 8. And what do you expect the probability to be? Well, 0.5. So what we're doing here is, instead of doing just one value, we're actually working out the cumulative value of all of these together, okay? So if I press equals on that, it's going to work it all out, and it actually gives you the values which you can see here. So 3.9 times 10 to the minus 3, which is actually equal to 0.0039. 1 is equal to 0.3, I don't know if you can see that. 1 is equal to 0.0352. 2 is equal to 0.1445. 3 is equal to 0.3633. So we've got all these values on here. They're all on here, and this is how you get them. Now, there is actually a table. Before this calculator, we had this calculator, we had like big lists of tables, and you had to go through the tables of values, and you had to go across and go down. And now you can do pretty much all on your calculator, which is really nice for you. So let's go back to this question and have a look at what they're actually asking. Now, notice that I've got all these values down on here. Okay. So what is the probability that we would see 6 heads or even more extreme values in is this significantly likely to support John's claim? So what he's asking here first, is 6 heads unlikely to happen? And if it is, does it fit in line with the 5% that we got, or the significance level of 5%, to say that the coin would be biased if I get 6 heads? Okay. Now, there is a problem with this, and the problem is that this data is discrete. Okay. Now, and it's also, if you notice here on this part here, it's the probability of getting x is less than or equal to x. Now, because we're dealing with everything which is higher than this, it says what does the probability would see 6 or even more extreme values. So we're looking at the probability of x being greater than or equal to 6. Okay. Now, the probability of something being greater than or equal to 6 using this table is the same as 1 minus the probability of this being less than or equal to 5. Now, the reason that's the case is because this is discrete. So because we're looking at this here being less than or equal to 5. So what we're saying here is that the probability of 6 is equal to the probability of everything happening which isn't that, which is the probability of being less than or equal to 5. Okay? Now, the reason that it's between 6 and 5 is because you can't get 5.5 heads, you can't get 5.6 heads, you can't get 5.7 heads, you can only get 5 or 6. So the probability of getting 6 heads is the same as saying the probability of getting 1 minus the probability of getting less than or equal to 5. So we've got our table on here, and again, remember, you could have got this from your calculator. So we've got our table on here. So the probability of x being greater than or equal to 6, in this case, is equal to 1 minus the probability of getting less than or equal to 5. And we can see from this table here, the probability of getting less than or equal to 5 is equal to 0.8555. Okay? So then I can do that on my calculator. Menu. There we go, back to 1. So 1 minus 0.8555. Well, the chances of getting 6 or more heads is equal to 0.1445, which is equal to 14.45%. So the chances of getting 6 or more heads is 14.45%. Now, actually, that is not within his significance level. His significance level says 5%. Okay, so the answer here is that this is the probability of it happening, of getting 6 or more extreme values. And actually, this does not support John's claim, because actually, this here is greater than the 5% that he wants. They've done it in terms of decimal there. But 14.45% is greater than the 5%. I'm going to write here significance level, just to make it really clear. Significance level, okay? So 5% is greater than the 5% significance level, which means that it doesn't support his claim at the moment. So if he was to do the experiment and he got 6 heads, then we can't say that the coin is biased, okay? So what is the probability that we would see 7 heads or even more extreme values? So that was part A. Part B now says, what's the probability of getting 7 or more? Well, we know that the probability of 7 or more, because it's discrete, is equal to the probability of 1 minus it being the probability of x is less than 6, okay? So the probability of getting 7 or more is equal to 1 minus. The probability of getting 6 in this case is equal to 0.9648. Okay, we can put that in our calculator. So 1 minus 0.9648, which is equal to 0.0352. In this case, it's equal to 3.52%. So the chances of us getting this, or 7 or more, is only 3%. Okay, so the chance of getting 7 or more heads, if I was to flick a coin, flicking my coin, if I was to flick it 8 times and I got 7 heads or more, could be 8, the chances of getting 7 or more heads is only 3.52%. Okay, so what I'm saying here is that the probability is so low under the significance level, which is 5%. Okay, he set that as 5%. It's so low that this coin must be biased. In that case, if I think about what I was saying, back to what I was saying before, I would reject H0 and I would accept H1 to say that yes, the coin is biased. This here, if I got 6 outcomes, I would say that the coin is not biased because it's not above the significance. Sorry, it's not below the significance level. However, this is less than 5%. Okay, significance level. Significant. In which case, it is very unlikely to happen. So it supports John's claim. Okay. So we've just worked that out here. Yes. So since this is less than 5%, it is very unlikely. So we reject the null hypothesis. We're rejecting H0, and we're saying that we accept the alternate hypothesis that the coin is biased. Okay. So these are our critical regions. So in which case, what we're saying here is that if you were to do the experiment and you flick a coin 8 times, if I was to get 7 flicks, then I'm saying that the coin, 7 heads, then I'm saying that the coin is biased. Okay. So, so in this case, the critical region is the range of values, and it's, again, this is in black, so it's worth writing this down. Make it big for you. So the critical region is the range of values of the test statistic that would lead you to rejecting H0. So in this case, make sure you get that down, please. Pause if you need to. In this case, your critical region is anything between 7 and the maximum number of heads, which is 8. So it's going to be, for this part here, 7 is less than or equal to x is less than or equal to 8. So our critical region is between 7 and 8. Okay, so we've done our test here. Yeah, so our critical region is between 7 and 8. So we don't need to do that again because we've already done it. Now notice the throw tip here from Dr. Frost. So use the first value after the one in the table that exceeds 95. Okay, so use that first one which exceeds 95 in this case. And the reason we're looking at 95 is because it's a 5% significance level. So I know that the probability of getting this one is 1 minus the one which is below it. Okay, so the first one which exceeds it, use the one after that. Okay, we'll come back to that in a second. So the critical values, I'll make this big again so you can see it. The values on the boundary of the critical region are called the critical values. So what is our critical value in this case? Well, I think that must be pretty obvious. Our critical value is equal to 7, which means that anything 7, that's the tipping point here. So 7 or above means that the coin is biased. Okay. So we're going to have a look at this one here now. So determine the critical region when we throw the coin, where we are trying to establish if there is a significant bias given the specific number of throws when the level of significance is 5%. Okay, so what we're looking at here is we are looking at critical regions. Now, they've actually given us 3 different options. Remember that with these, you might want to write them out from our calculator. So we can click on menu, we can click on 7, which is statistic. We click on binomial CD. We're thinking about the list now. We're not just thinking about one value, we're thinking about a range of lists. So for 1, because it's only 5 in that case, we're going to look at all 5. So looking at the probability of getting 0 heads, of 1 head, of 4 heads, of 1 head, of 2 head, of 3 head, and of 4 heads. We don't need to do 5. I will do 5 because you'll see that it's 100 anyway. So there's all our list there of all of them. We then press AC, which goes back to the top. We then press equals, and now we're going to say what our population parameter is. So we're going to say that n is equal to 5 throws. I'm going to say the probability of getting the heads is 0.5. We press equals, and it'll give us our probabilities, which notice is the same here as the ones we've got. So I don't know if you can see that. So here we've got, you can see that here. It does say 0.0312, which is our first one, 0.1875, which is our second one, 0.05, which is our next one, 0.8125, 0.9687, and the last one is obviously 1, because the probability of getting all of these things happening, everything, remember this is cumulative, so it's everything happening below 5, which is 0, 1, 2, 3, 4, and 5, probability of everything happening, it must be 1, okay? So, if we're looking at our first one here, what is the critical region? Now, I'm just going to flick back so you can remember what the tip was. Because he says that it's a 5% significance level, you use the first value after the one in the table that exceeds 95. I'm going to suggest that you write that down. That is really important. If you're looking at the top end, so at the top, if you're looking at your largest, what am I trying to say? If you're looking at your maximum extremity, so your max extreme values, so anything which is greater than, then we use this tip here, which says use the first value after the one in the table that exceeds. Now I'm going to change that to, instead of 95%, to say 1 minus your significance level, okay? Or 100% minus that, okay? I probably should have put percentage there. So maybe 100%, 1 minus your significance level as percentage. Does that make sense? So that's if we're looking at the top end. However, if you're looking at the bottom end, so your minimum extreme values, in which case being biased towards tails, we don't do that. We're just, because it's less than, we just look at the first value which goes below our significance level. So if you are looking at your minimum extreme values, if you're looking at your minimum extreme values, we don't need to do the one above, okay, because we're looking at everything that's less than. You use the first value that goes below your significance level percentage. Okay, we use the first value. Now these two here, if you get that down and if you understand that, then this becomes a lot easier, okay? These two here are really, really, really important, okay? So if we're looking here at our critical values, let's have a look at this one. So here what we're saying is, what's my critical region? Well, the first one says a coin is thrown 5 times, trying to establish if a coin is biased towards heads. So if it's biased towards heads, now we don't need this in our first one. I'm going to keep that there because we are going to need that. I'm going to put this to the side actually. Okay, if the coin is biased towards heads, we know that our original hypothesis would be that your probability is equal to 0.5. Now they haven't done this, but I'm just going to do it to make sure that we understand it. Our alternate hypothesis is that the probability is going to be greater than 0.5. Okay, so the question says, what's the critical region for this? Now remember that we are looking for the 1. So use the first value after the 1 in your table, which exceeds 1 minus your significance level. So our significance level in this first one is, in this question is 5%. So we're looking at the first one, which exceeds 1 minus 5%, which in this case is 95%. So we're looking down this list, okay? We're looking down this list. So the one which exceeds that is equal to that 96% there. So the first one which exceeds 95, so our probability of the one exceeding 4, which is going to be probability of greater than or equal to 5, is equal to 1 minus the probability of x being less than or equal to 4. So our first one is 4. You can see that 4 exceeds 95% or 0.96%. So in which case our critical region is going to be anything which is above that, which is greater than or equal to 5. So this is equal to 1 minus 0.9688, which is equal to 1 minus 0.9688, which is equal to, again, it's going to be to this 0.03. So that's the first one that goes below 5%, and actually the percentage is 3.12%, which is less than 5%. So that's our critical region. So in which case, our critical region in this case would be anything which is 5 or above. But because I'm only doing it 5 times, it means that it's just going to be equal to 5. So our critical region in this case is 5. Okay. That was our first one, part A. I'm going to try and shorten this a little bit. So a coin thrown 10 times trying to establish a bias towards heads. So again, the bias towards heads, so it's going to be exactly the same starting point of this. But remember, we're using which is the first one that goes over 1 minus our significance level. So over 95 in this case. So I'm going to go down my list. I'll make it big so you can see it. So the first one that goes over it, well, I'm going to go down, 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 down. The first one that goes over it is this one here, okay? This is the first one that goes over, okay? So when I'm going over that, the first one that goes over is this one. So remember, it's one above that, okay? It's the one above that we think about. So the probability of x being greater than or equal to 9 is equal to 1 minus the probability of x being less than or equal to 8. Now this is the first time that it goes over that, which is equal to 1 minus 0.9893, which in this case, 1 minus 0.9893 is equal to 0.0107, which is equal to 1.07%, which is less than 5%. Now, just for a little side note, so our critical region in this one is going to be equal to between 9 and 10, or x is equal to 9 in this case. Okay. Your critical value is going to be equal to 9. Your critical region is equal to 9 is less than or equal to x is less than or equal to 10. So if you were to do the test 10 times and you get between 9 and 10, it means that the coin is biased. Okay, I'm just going to show you why this kind of works. Because you might say, well, 94, why doesn't that one work? Well, if I think about the probability of x being greater than or equal to 8, the probability of x being greater than or equal to 8 is equal to 1 minus the probability of x being less than or equal to 7. And the probability of that happening is equal to probability of less than or equal to 7 is equal to 0.9453. So 1 minus 0.9453 is equal to, the probability of that is equal to 0.0547. So it's actually 5.47%, which is greater than a significance level. So it can't be 8 and above. Sorry, it can't be 8 and above, because actually the probability of that happening is 5%, okay, which is bigger than what I want. So our critical region for this is this one here. Okay, I just showed you that as a little kind of side note. Right, on to this last one here. The probability a coin is thrown 10 times and trying to establish if it's biased towards tails this time. Now, I'm just going to do the start of this one. So my original hypothesis, this case, is the same, a population parameter, which is a coin has got a probability of heads of 0.5. My alternate hypothesis this time is that the probability of this happening is biased towards tails, which means the probability of this must be less than 0.5. Remember, this is the probability of getting a heads. So if it's biased towards tails, it means that my probability of this must be lower than 0.5. Okay? Now, we're not looking here at the extreme values at the top end. We're looking at if it's biased towards tails, then we're not expecting to get more heads. We're expecting to get less heads. Okay? So we're looking at the bottom end of this. And if I go back to this part here, this is the most important part. If you're looking at the minimum extreme values, use the first value that goes below your significance level. So what's the first value that goes below 5%? Well, my first value that goes below 5%, I'll make it big so you can see it. My first value that goes below 5% in this case is equal to this one here. Okay, that's above 5%. So my extreme values are anything which are 1 and below. So my first value below my significance level of 5% is probability of x being less than or equal to 1, which is equal to 0.0107. So actually the probability is 1.07%, which is less than 5%. That's the first time that it goes below. So my significance level, my critical region here is anything which is below 1, in which case that can be 0 and 1. So it's going to be 0 is less than or equal to x is less than or equal to 1. So this is now my critical region. Okay, it works the other way, the other way around. Okay, so we're just seeing when it goes below our significance level. So we've got another question here. Let's have a look at these ones here. So we're changing it now away from coin. We're having a look at probability of something else happening. So we've used coin quite a lot. So John wants, no, it's towards a coin again, sorry. The next one's not. So John wants to see whether a coin is unbiased or whether it is biased towards coming down as heads. He tosses it 8 times and counts the number of times x it lands on heads upmost. What value would lead to John's hypothesis being rejected? Okay, so what we're saying here is what value is below the 5% significance level, which means that this would be rejected. Now, the way I do this is I'm going to go down here. I'm looking for the first one that goes above 95%, because my significance level is 5%. And that case here is 6. Okay, 6 is my first one. So I know I'm going one above that. So in this case here, we ensure that the probability is, so my probability, sorry, I should have made this big so you can see it. I'll give you a second just to get it down if you need to. So with this one here, my probability, the first time it goes over 95% is that 6 value. So it's going to be the probability of x, the probability of x being greater than or equal to 7 is equal to 1 minus the probability of x being less than or equal to 6. So the first time it is that is 1 minus the 0.9648, which is equal to 1 minus 0.9648, which is equal to 0.0352, which is 3.52%, which is less than my significance level of 5%. So that's the first value. So my critical region is asking for in this case. What values would lead? So my critical region would be 7 is less than or equal to x is less than or equal to 8. My critical, what values would, the values would be 7 and 8, wouldn't they? So let's just have a look at that. Brilliant. So the values would be 7 and 8. So what we've looked at here is the 7 and 8, but we can also find out the actual significance level. So the actual significance level is the probability of it actually happening. So we've set the critical region as 5%, but there's a big difference there between 5% and the 3.52%. This is my critical region. This is the probability of it actually happening, and there's no kind of in between. So this is my significance level, but this here is the probability of getting 7. The probability of getting 6 is going to be 1 minus 1, 5. So 1 minus 0.8555. I'll just write that down in green so you can see it. So the probability of x being greater than or equal to 6 is equal to 1 minus the probability of x being less than or equal to 5, which is equal to 1 minus 0.8555, which is actually equal to 0.1445, which is 14.45%. So this is the probability of getting greater than or equal to 6, and this is the probability of getting greater than or equal to 7. And we know that our critical region is this part here, but the actual probability of it happening is this. So when I set my critical region, well, actually, when I'm asked the question, what's the actual significance level? Well, the actual significance level is this part here. This is the actual probability of getting within that region, if that makes sense. So my actual, remember to get this down, I'll make it big so you can see it. So the actual significance level is the actual probability of being in the critical region. So the probability of being in the critical region isn't 5%. The probability of being in the critical region is 3.25%. So we've set the critical region as 5%, but the actual probability of it happening is this 3.25. Okay? Brilliant. So this is our critical region, but this is the probability of it actually being that. Okay? So suppose I throw a coin 8 times and was now interested in how many heads would suggest the coin is biased, either way. So now we're not looking at one way or the other, we're looking at both ways. This is actually called a two-tailed test, okay? Now this is where things kind of diverse again. So with this one, instead of just looking at one end, so we're saying it's biased towards heads or it's biased towards tails, what we're actually saying is that I don't know whether it's biased towards heads or biased towards tails. I just don't think the probability is 0.5. So this is what's called a two-tailed test. So if I've got a significance level of 5%, and I'm not sure whether that's at the top end or at the bottom end, what you've got to do is you've got to split that and do it half of it at the top and half of it at the bottom. Okay, and then you use that to do your test. So in this case here, we split it into 2.5. I'm going to make this big for you so you can see it. So suppose that I threw the coin 8 times and was now interested in, I was now interested in the amount of heads would suggest that it's a biased coin. So either way, so either being tails or being heads. How do we work out the critical values with a significance level of 5%? So what we do is we split our significance level 5%, so it's 2.5% on the bottom end and 2.5% on the top end. So we're splitting that in half. So what we're looking at here is the first time. So it's probably worth writing this down actually, for a two-tailed test, with significance level of 5%. Now, a two-tailed test is where we're checking the top and the bottom. So what's the critical region for the top and the bottom? We split 5% for the top and bottom. So 2.5% each way. So 2.5% each way. And then we test for that there. So instead of looking for 5% at the top or 5% at the bottom, which is what we did before, we're looking at 2.5. The critical region is going to be the first time it goes below 2.5 at the bottom end, or one after, the one where it goes over 97.5, okay? So for the positive tail, in this case for 8, so for the positive tail, we're looking, so for the positive tail, so when it's greater than, we're looking at when does this go above, when does it go above 97.5? So here we've got our, so we've got our test here. So instead of looking at just the top end, so for tails, or just the top end for heads, or just the bottom end for tails, so we're looking at both sides now. And that 5%, which I was working with before, has had to be split into 2.5% at the bottom end and 2.5% at the top end. Okay, so we're looking now for both sides. We're looking for the first time we go below 2.5%. That's going to be your critical region for that one. And we're also looking for the first time we go above 97.5%. And we're going to go, remember, we need to go the one above that, okay? So we need to go one above that value, okay? So we're finding the critical region for both ends now. So remember, you could have done this in our calculator, so I put it in for our table. So probability 0.5, there's 8 outcomes, I'm looking at all of them. So when's the first time that I go below 2.5? Well, if I look at 1 here, the first time that I go below it, that's 3%. Make this big so you can see it. So 1 is 3%, which is not below the 2.5. However, this one here is below the 2.5. So our critical region at the negative tail is going to be equal to this part here, which is 0. For the positive tail, I'm looking for the first time that it goes above 97%. Well, 6 is 96%. 7 is over 97%. Remember, we go 1 above that, okay? So it's going to be 8 is our critical value for that one. So for the positive tail, the first time it goes over 97 is 7. And we remember we're going to go 1 above that because of what we're doing. So it's equal to 8, okay? I'll show you the reason for that. I'll just show you the maths. So just very quickly, we're looking at the first time it goes below 2.5. Well, that's when our probability of x is less than or equal to 0, which is equal to 0.001. 0.0039, which is 0.39%. So actually, the actual critical region, sorry, the actual significance level is actually really small, okay? So that's for the bottom end, so anything that's less than or equal to 0. For the top end, we're looking at the first time it goes above 0.95 and then 1 above that. So the first time it goes above 97.5 is 7. So the probability of being greater than or equal to 8 is equal to 1 minus the probability of being less, the x there, x is less than or equal to 7, which is equal to 1 minus 0.9961. So 1 minus 0.9961, which is really small. I think that actually similar to this, it's the same, which is also 0.39%. So these are our two extreme values. So our critical region for this two-tailed test is 0, anything that's below 0 or anything that's above 8. Now obviously you can't get below 0 and above 8, but it includes 0 and it includes 8. So our actual critical region for this is 0 and 8. So if I was to flick a coin flick a coin 8 times and I got 0, and I was to flick a coin 8 times and I got 8, then I would say that this coin is biased. Okay? So notice here you've got, this is actually a really good little picture here. So here we've got the critical region. Can I zoom in on that? No. So here we've got our critical region, which is 0. We've got our accepted region here between 1 and 7. And then we've got our critical region at the top, which is 8 as well. So this is now a two-tailed test. Okay. So we'll have a go at this question together. A random variable x has a binomial distribution of 40, p, which means that I'm doing the test 40 times. Okay. A single observation is used with a hypothesis h0 is equal to p is 0.25 and a alternate hypothesis as probability is equal to is not 0.25. Using a significance level of 2%, find the critical region for this test. The probability in each tail should be closest, so it should be the closest to 0.1. So it's not saying here now it's got to be below 0.2%. It's saying whatever value is closest to 1% because we split it. So write down the actual significance level of this test. So I think that from what is said here, there is actually the mistakes in this textbook. So we're just going to go through it with what we've got. So get that down in your notes. I'll give you a second to get that down. Okay. So a random variable x has a binomial distribution of 40, p. So what we're saying here is that we're doing something 40 times, all right? A single observation is used as a test. So we're giving our null hypothesis. In this case, our null hypothesis is that h0 is that the probability is equal to 0.25. Okay, that's our original hypothesis. We're saying that we don't think this hypothesis is true, in which case we're not saying it's positive towards the top end or positive towards the bottom end. We're just saying we don't think it's true, in which case we're saying our alternate hypothesis is that the probability is not 0.25. Okay? Using a 2% significance level, find the critical regions for this test. The probability in each tail should be as close to 0.01 as possible. Okay. So the first thing we need to look at is because we've got a 2% significance level and it's a two-tailed test. So I'm going to even write this down, two-tailed test. So 2% divided by 2 is equal to 1% at each end. This is what we're looking at. We're looking at 1%. We're trying to find out where my values are 1% at each end. Okay. So the first thing I would do with that is I would get my calculator and I would do my list on my calculator. So menu, 7 statistic, okay? I'm going binomial CD, so cumulative, which is there. And I want to find a list of these, so I'm doing the list value. Now, you could put all of these in there, but you know that somewhere in the middle, in fact, we can actually find out what our expected value is. It's probably worth showing you how to do that. To find out your expected value, the expected amount of times that this is going to come up, you would do 0.25 times by the amount of times it's happening. So we'd expect it to be about 10 times. Okay, that's what we'd be expecting it to be. So let's go back to 7, normal distribution, CD. We're doing a list. We're checking several values. We're not just checking one at a time. So in the list, now they've only done it from 2. Now they probably, Dr. Frost probably knows what to do here. I would have started at 0. So I've done 0, I'll do 1, I'll do 2, I'll do 3, I'll do 4, and I'll do 5. Okay. So I've done between 1 and 5. Now I'm not going to type in 1 to 40 in here. Okay. But I am going to look at the kind of the extreme end of this. Now, I said to you that the probability of this happening was 10. So I want to be kind of the other side of that. Now, I could type in here 20, 25, 30, because it does go all the way up to 40, doesn't it? B40 means that I'm doing it between there and 40, but I know that for my expected value, which is 40 times by the probability, so 40 times by 0.25, that my expected amount of outcomes is 10, okay? So actually, I'm going to go just a bit above that, and they've actually done it between 16 and 19. So you can see. Now, you could have put all of them in here if you wanted to, just to see where it gets to the extreme values. But I'm just going to put it in the same then, 16, 17, 18, 19, like so. I press AC, I press equals. I know I've got 40 different, 40 different, doing this 40 times, and the probability of it happening is 0.25. So I'm going to put that in there, and I've got all these values here. So what I'm looking for here is, now you've got to be careful with this, because it says the closest to 0.1, it's actually not saying below 0.1. But I am going to look at the one which goes below 0.1. So for my tail end, okay, and then for my top end, so what's the first time that we go below 1%? Well, we go below 1% between 4 and 3, don't we? Let's get that big there. So we go below 1% between 4 and 3. Okay, so between there we go below 1%. Okay, so between these two. Now, which one of those is actually closer to 1%? Well, it actually is 3, so we're all right there, aren't we? Because that one's closer. It's the first time it goes below 1%, and it's equal to, and it's closer to 1%. So with that one there, to find my critical values, the probability of x being less than or equal to 3 is equal to 0.0047, which is equal to 0.47%. So that's the first time that I go below 1% on the bottom end. Okay. Now I want to go the other way. Now remember, you were looking for the first time you go 1. The first time I go above 1 minus the significance level. So 100% on 1 minus 1%. The first time I'm going to go over 99% or over 0.99. That's what I'm looking for. Whereas the first time I go over that. Now, we're looking at that, but we've also got to think about the fact that this says here, it should be as close to 0.01 as possible. So it's not saying that it needs to go, what's the first time it goes above it, it's saying what's the closest one, okay? Now, I'm just going to come back to that in a second. So the first time that I go above is for 17. So the probability, remember I go 1 above, so the probability of x being greater than or equal to 18 is equal to 1 minus the probability of x being less than or equal to 17, which is equal to 1 minus 0.9953, which is equal to 1 minus 0.9953, which is equal to, it's actually the same as this, the 0.0047, which is equal to 0.47%. Now, this here is the first value that goes below 1%. However, it's not asking for that. It's asking for the value which is closest to this. If I look at the one before it, so if I look at the probability of this being greater than or equal to 17, then what I get is 1 minus the probability of being less than or equal to 16, which is 1 minus, what is the probability of 16? So 0.9884. So 1 minus 0.9884 is actually equal to 0.0116. So the probability of this is 1.16. Now, because this question here says, what's the probability? Sorry, find the critical region, and the probability in each tail should be as close to 0.01 as possible. Well, if it was saying the first time it goes below it, then we'd use this one here, because this is the first time that we go below 1%. But it's not asking that. It's asking for the one which is closest to 1%, which is actually this one, okay? So we're using everything which is 17 and above. So our first part here now says, what is actually our critical region? Well, our critical region is everything which is less than 3%. Sorry, less than 3%. Less than 3, which is between 0 and 3. So what's the probability of this being less than 3? So our critical region for this is between 0 is less than or equal to x, is less than or equal to 3, or anything which is above 17, and it's above 17 because it's closest to 1%, okay? If it didn't say 1%, and it said make sure that you're in the critical region, then you'd just be looking at this one, in which case it would be above 18. Because it says closest, it means that it's this one here. So in which case, all 17 is less than or equal to x, is less than or equal to the maximum which it could be is 40. So these two here are our extreme values, which means that the probability of this can't be 0.25. So there's part A. So the next part, part B, says that write down the actual significance level of this test. Well, the thing is we need to think about here, what is the probability of this happening? Well, we did work that out, didn't we? The probability of this happening is here. Let's do that in red so you can see it. The probability of this happening is this one here. The actual significance level of this is 0.47%. And what's the probability of getting this? Well, the probability of getting this is, where is that? It's here, isn't it? The probability of getting greater than 17 is 1.76. The probability of getting these here is 1.16%. Okay? So the probability of getting this is this. The probability of getting this is this. Okay? So my actual significance level is those two added together. So 0.47% plus 1.16%, which is equal to 0.47 plus 1.16, which is equal to my actual significance level is 1.63. And the reason it's 1.63 is because actually you can only get those values on this side, you can only get those values on this side. So this is going to be below our actual significance level, which is 2%, but this is the actual significance level it's going to be. So that's that question done there. Brilliant. So what I'm going to suggest you do is now have a go at this, this section here on critical region. So it's page 103 to 105. It's quite a big exercise, okay? do make sure you're having a go at all of these. This is a tricky task. It's taking me now an hour and 20 minutes just to do this first part. In the next part, we're going to be looking at actually doing hypothesis tests. I'd suggest that you pause, you have a go at some of these questions, you make sure you're getting all these notes down, because this is tricky, okay? And the only way to learn maths is to do it. The only way you're going to understand it is if you keep having a go at these questions. So thank you for watching this video on the first part of hypothesis testing. Make sure you are having a go at these questions, because the only way to learn maths is to do it, and have a lovely day.